Related rate problems give us the opportunity to apply the concept of implicit differentiation. The easiest way to talk about related rates problems is to actually look at a particular question and then kind of explain how it works as we go. So for this first question we have that a circle has an initial radius of 50 feet when the radius begins decreasing at the rate of 4 feet per minute. So what is the rate and change of area at that instant when the radius is 12 feet? So we have two things that are changing. If we think about the radius of a circle, we'll say this is at the beginning when the radius is 50 feet. We can see here that the area is pi r squared, of course. Radius is 50. 50 squared is 2500, so this is 2500 pi feet squared. Now it says when the radius begins decreasing, so that tells me that the radius is getting smaller, so our next circle would be smaller. And here the radius is 12 feet. So again, my formula A equals pi r squared. A equals pi times 12 squared. A equals 12 squared is 144 pi feet squared. So we can see that the area is much smaller for the circle with a smaller radius. So we have two variables that are changing. Radius, and then because the radius is changing, so is the area. So we kind of have to keep track of two things, and they're both changing with respect to time. So there's time that's changing as well, that's our variable of interest. Now it says, what is the rate of change of area at the instant the radius is 12 feet? This is just telling me my area. It's not telling me the rate of change of my area. So this circle, the larger one and the smaller one, are just showing me how area is affected by the radius. So let's go ahead and start setting up the actual question. To get started, we can use an equation relating the area of a circle and the radius. So let's go ahead and start with the formula. A equal pi r squared. Then what we can do is we can find the related rate equations by taking the derivative with respect to time. So I'd take dA dt of both sides. And I shouldn't say dA dt of both sides, we'd be taking d dt of both sides. And on the left hand side it turns out to be dA dt. So this is how I can come up with the related rate equations. Now on the left hand side I just have dA dt. Now on the right hand side, pi is just a constant, so I just drag it along. And then r squared, the derivative of r squared is 2r, so I get pi times 2r. And then I just took the derivative with respect to a variable other than t, so I need to tack on that dr dt. So rewriting, I get dA dt equals, just to clean this up a little bit, let's pull that 2 out front, 2 pi r dr dt. Now this isn't my answer, but this is something very important. This is our related rates equation. So this is showing me how one variable changes with respect to the other. So as area changes, radius changes, or as radius changes, areas change, vice versa. Now I'm talking about the rates as well, because we have dA dt, so as the area changes, so does the radius, and this is kind of that constant that we can look at. Now we were given some other information as well. We were given when the radius begins decreasing at the rate of 4 feet per minute. Okay, so this business, decreasing is important, and 4 feet per minute. So let's take this information and let's write something about that. It says the circle has an initial radius of 50 feet when the radius begins decreasing. So the change in radius with respect to time. So this is dr dt is equal to -4, and it's important to include units. Always include units throughout the problem, because if units don't cancel correctly, it's a good indicator that I have a mistake. So it's a good way to check your work. So we have this equation that's going to be important, dr dt. Now this fact that we have an initial radius of 50 feet doesn't really even end up coming into play here, So this is kind of a red herring. A lot of times some of these problems will have that. It doesn't end up mattering. It says, what is the rate of change of area? So we're looking for dA dt. So we're looking for dA dt at the instant the radius is 12 feet. Okay, so let's come down here and use our related rate equation. So dA dt, and that's what we're trying to find from up above, is 2 pi, r is 12, and then dr dt was -4 feet per minute. Now I just got done saying how important it was to use units, and then I forgot to use them. So let's put in, this should be 12 feet. Now a lot of times in some of your homework problems they'll mix miles per hour and meters per second, so you have to make sure you're using all the same units. So as we solve this, then we have 2 times 12 is 24. 24 times 4 is a -48. Sorry, that's 2 times 12 is 24. 24 times 4 is 96, but it says a negative. So this is -96 pi. Now let's look at our units. I have feet times feet, so I should have feet squared here per minute. And that makes sense because the radius is in terms of feet, but area is in terms of feet squared. So this is saying the area is decreasing, this is dA dt, at that instant, -96 pi feet squared per minute. Now for this homework assignment, you're going to definitely want to have a calculator out. On your exam, though, you won't have a calculator, so you'll be able to set up a problem but not maybe solve it. So you should be able to do a problem like this up to this point, but if your homework asks you for a decimal approximation, that's something you definitely wouldn't be expected to do on a homework assignment. If you are asked to do a decimal approximation in your homework set, make sure you look at the instructions to see how you should be rounding. So for this one, let's say you were asked to round to the nearest hundredth. So this would be the same answer. This would be an exact answer. This answer would be rounded to 2 places. So just make sure you very clearly read those examples. So this is an example of related rates. Radius is related to area. And when we set up our related rates equations, I always start with some sort of an equation that's familiar. Some of them are geometric equations. Some of them you might have to look up. Volume of a sphere, volume of a cylindrical solid, things like that. But then when we start taking derivatives, it's important to know what we're taking the derivative with respect to. So let's go ahead and work quite a few more of these problems. So for our next problem, again, let's go ahead and start with the idea of coming up with a formula that describes the problem and then thinking about some implicit differentiation. So we have a spherical balloon, so this would be like a basketball, something with 3 dimensions. So we have a spherical balloon is inflating with helium at a rate of 80 pi cubic feet per minute. So this is really volume that we're looking at here. So this idea is volume. So this is going to be the change in volume over time. So this is dV dt is what we kind of want to think about there. So with dV dt, I can say that dV dt, it's inflating, so it's going to be positive, is 80 pi cubic feet per minute. And that's cubic feet. And that green is kind of hard to see, so let me update that to make it red or purple. Okay, so that's our first piece of information. It says, how fast is the balloon's radius increasing? So we want to know how fast the radius is increasing, which would be dr dt. So this is our unknown. This is what we're looking for. And it says at the instant the radius is 2 feet. So here we know r is 2 feet. Now dr dt, we can talk about units in a little bit here. When we end up solving, we'll see what the units are. But this is kind of where we can start. So to get started, we need the volume of a sphere. Now if you don't know the volume of a sphere off the top of your head, the volume of a sphere is going to be equal to 4/3 pi r cubed. And again, on a test, You won't have access to a calculator, but you should be able to at least set up one of these problems and take the derivatives for the related rates. But I wouldn't expect that you would be able to plug in large numbers and things like that, or find a decimal approximation to 80 pi. So this is where we'll get started. Next step, we would go ahead and take the derivative of both sides with respect to time. Okay, so we want to know how this is changing with respect to time. So this would look like d dt of v on both sides. So d dt of 4/3 pi r cubed on both sides, or on the right side. Okay, so now as we take those derivatives, on the left hand side I have just straight dv dt. Now on the right hand side I have the 4/3, and then remember I bring the 3 down, and then I have my pi, of course, and then I decrease the exponent by 1. And I just took the derivative with respect to a variable other than t, which is my variable of interest. So remember, I have to use that implicit component and multiply by dr dt, because I took the derivative of r with respect to t. Now what we're trying to solve for is dr dt. So I'm not trying to find dv dt, I want to find dr dt in this case. Well, I have some canceling that occurs here, so that's nice. And then I can either plug in or I can solve for dr dt right now. I'm going to rewrite first and then probably solve. So I have 4 pi r squared dr dt. So plugging in, I know dv dt up here was 80 pi. And then remember, I want to keep my units with me because they're going to make sure that everything is canceling correctly. And this equals 4 pi, and radius in this case is 2 feet. I want to make sure I have my units in there. And then dr dt is my unknown. This is what I'm trying to solve for. I want to know the instantaneous rate the radius is increasing as it's being filled up and the radius hits 2 feet. So one thing I need to make sure I have here, this is radius squared, so let's go ahead and put that squared up here. Okay, so simplifying a bit, we have 80 pi cubic feet per minute equals, so 2 squared is 4, 4 times 4 is 16 pi square feet, and of course dr dt is what I'm trying to solve for. Now if we want to get dr dt by itself, I would divide both sides by 16 pi square feet. And of course on the right hand side I have this canceling, and then I'm left with dr dt equals, okay, so we have 80 divided by 16 is 5, pi divided by pi cancels, and then feet cubed divided by feet squared cancel into feet per minute. So the radius at that instant is changing at 5 feet per minute. So again, a problem like this, you could be expected to do this on a test, because you can see that the actual number crunching is very small. I wouldn't expect that you should be able to come up with some decimal approximations though if needed. So as long as the number crunching is small, it's a reasonable type of problem to have. Okay, let's go ahead and look at another example. I want to make sure you have enough examples to go off of for your homework. That's looking at a cylindrical solid, or looking at a cylindrical chamber like a piston. So let's go ahead and look through this one and see if we can draw a picture that might help us out here. We have a piston is seated at the top of a cylindrical chamber. So just a rough sketch of a cylindrical chamber would look something like a roll of paper towels. So this would be like a cylindrical chamber. It has a radius of 6 centimeters. So our radius here is 6 centimeters. Now that's constant. A cylindrical chamber doesn't get wider. The only thing that happens with the cylindrical chamber is the piston on top moves down toward the bottom and then comes back up. So that 6 centimeter radius, this is constant. It's not variable. Now other things will change, but that radius doesn't change for this example. It says with radius 6 centimeters, when it starts moving into the chamber at a constant speed, so the speed is even constant here. So another one that we can talk about is the change in height basically over time. So we're looking at changing at a constant speed. So the change in height, because what's happening, and this is not going to be the best drawing, but there is a piston coming through here and it's moving downward, and it goes up and down to in your engine. So as that's happening, this is kind of like the height of that piston. So the change in height with respect to time, then they're saying is constant, and it's moving down. So it's a -2 centimeters per second. So that's our dH dt. And again, it's moving down, so that's why we have a negative sign here. Now let's see what other number we have. What is the rate of change of the volume? So we're looking for rate of change of the volume is equal to the change in volume over time, dV dt, of the cylinder when the piston is 3 centimeters from the base of the chamber. Okay, so then we're looking at something about 3 centimeters from the base of the chamber. So let's figure out where that comes into play. Now as we look at our picture and we talk about 3 centimeters from the base of the chamber, that doesn't really end up mattering at all. It doesn't tell me how far I've traveled when I talk about 3 centimeters from the base, because I would have to know the overall height of the piston. So this bit about 3 centimeters from the base of the chamber, there's some information there, but it's not really anything that's going to end up being useful for what we have. So the thing we want to start off here is the volume of a cylinder. So this is another formula that would be handy to know. And the way I can remember this one is the circle on the end is pi r squared. And then I just have stacking these up to a height of h. So my volume of a cylinder is pi r squared h. Now I want to find the related rate equation by taking the derivative with respect to time of both sides. Now we have something interesting going on here on the right hand side, because we have two variables. We have an r, we have an h, we have a t, and we have this pi. Well, pi is a constant, and for this problem r is also considered a constant, but we won't worry about that right now. I'm going to plug that in a minute. Right now we want to find our related rate equations. So on the left hand side I would have dV dt, and on the right hand side, again, pi is a constant, r squared is a constant, so both of these are constant. So I just have pi r squared, just drag along those constants. The derivative of h is 1, and then I took the derivative with respect to a variable other than t, so I tack on that dH dt. So here we have pi r squared dH dt. Now what my unknown is, this is my unknown up here, is this dV dt. So I'm trying to figure out what dV dt is. So I just go ahead and plug in. My radius, and remember I'm going to use units here, is 6 centimeters. And this is r squared. dH dt, I think we came up with the value for that, was -2 centimeters per second. So simplifying, I end up with dV dt equals, okay, so 6 squared is 36. 36 times -2 is -72 pi centimeters cubed per second. Now this makes sense to have centimeters cubed because I'm talking about volume, and volume is three-dimensional, so centimeters cubed makes sense here. Now if I was trying to find a decimal approximation, so this would be my exact solution. If I was trying to find a decimal approximation, we could say that dV dt then would equal -226.19, and this would still be centimeters cubed per second, but this would be our rounded to two places. So you always have to look at the directions to see exactly what problem they're looking for, or what solution they're looking for. Are they looking for an exact solution or a rounded solution? So we kind of have some ideas about how related rates work. In this case, my related rate were time, the radius was constant, and the volume that was changing based on the height and the radius of the piston. Okay, let's go ahead and look at another example. So again, units are very important here, and also reading the instructions to see if they're looking for an exact or a decimal approximation for the solution. Okay, this one, the formula is not too difficult to come up with because we're looking at a rectangle. So a rectangle initially has dimensions of 3 centimeters by 4 centimeters. So let's go ahead and start with that. And for a rectangle, we'll call this a base of 3 centimeters and a height of 4 centimeters. And I know that this is not to scale. This looks longer, so this should be the 4 and this should be the 3, but it doesn't matter. We just have to make sure we establish base and height here. It says all sides begin increasing in length at a rate of 4 centimeters per second. So what we're looking at here, increasing in length. So the base ends up changing 4 centimeters per second, and so does the height. So the change in base with respect to time is equal to 4 centimeters per second, and the change in height with respect to time is also 4 centimeters per second. And that's this information right here. All sides, whether they be base or height, is increasing. It says, at what rate is the area of the rectangle changing? So this is the change in the area with respect to time. So this is our unknown. This is what we're trying to figure out. And they give us some information here about t equals 15 seconds. So apparently we need some sort of a formula to start with. So the area of a rectangle, and again, this is our nice easy formula. So the area of a rectangle here is A equals base times height. So I need to take the derivative of both sides to come up with my related rate equation. So that would be dA dt equals the derivative with respect to t of base times height. Well, this is a product rule. I have two functions multiplied. I don't have a constant here because base and height are changing. This is how they're starting initially, but they're growing. So this is the product rule. So this is going to look like dA dt equals. Now if you remember the product rule, it's the first function times the derivative of the second function, which would be dH dt here. Because I'm taking the derivative of h as 1, and I took the variable, or the derivative of the variable with respect to time, so I need to tack on that dH dt, plus the second times the derivative of the first, which would be dB dt. So this is my related rate equation. Now, related rates equation, because base and height are changing. I wonder if I noted that up here. Yeah, I didn't note that, so let me plug that in here real quick. This is our related rates equation. I think I did on our others, but just let me double check. Because a lot of times what they are asking for is specifically that related rates equation. So I want to make sure that you know which one that is. Okay, so we've got those fixed up. Let's kind of go back where we were at. So this is my related rates equation, all of this right here. So, and actually this dA is part of that as well. So what I have is I want to know dA dt, that's my unknown. Now to figure out what dA dt is, I need to figure out what the base is. But the key to this is the base isn't 3. I need to know what the base is at 15 seconds. So it would be 3 plus 15 times 4 centimeters per second. And this would be 4 centimeters plus 15 times 4 centimeters per second, because it would have grown. So 15 times 4 is 60, so this would be 63 centimeters at 15 seconds. And this one would be 64 centimeters at 15 seconds. So that plugs in down here, so my base is now 63. My height is now 64. And actually I'm going to plug in a little bit more info here. I want to make sure I don't drop my units. So 63 feet plus 64 feet. Now I need to know what dH dt and dB dt are, and they're right up here. They're both 4 centimeters per second. Okay, and I definitely have my wrong units here. These are supposed to be centimeters. I can see right up here, so centimeters. And this will be my solution. So dA dt, the change in area with respect to time at 15 seconds, we take 63 times 4, and what would that be? 6 times 4 is 240, 252 centimeters squared per second. Okay, and then 64 times 4 would be 240 plus 16 would be 256 centimeters squared per second. And then we add those together, and 252 plus 250 is 500. This looks to be 508 centimeters squared per second. Okay, now this one is already in exact form, but this makes sense because area is in terms of centimeters squared. So my units are centimeters squared per second here, and that's how the area is changing. So, as usual, make sure you set this up. This would be a very reasonable problem to do on an exam because we don't have any huge numbers here that I need to crunch. Let's go ahead and look at one that takes into account Pythagorean's theorem. So this one is kind of a famous bit of a problem. It's the sliding ladder problem. So we have a ladder, and it's 10 feet tall, and it's leaned up against a vertical wall, and that's what creates our triangle here, and it in fact creates a right triangle. So let's go ahead and draw that picture. We have a wall, and the height of the wall really isn't that important as long as it's tall enough for the ladder to lean up against. And we have this ladder leaning up against the wall. And of course, with the ground, this would form a right triangle if this wall is straight up and down. So we know one piece of information here for sure. We know that this is 10 feet tall, or 10 feet long, this ladder is. Now it says, when John begins pulling the foot of the ladder away from the wall at a rate of 0.6 feet per second. So if we think about what is changing here, we'll call this x and this y, just because that's usually our horizontal and vertical values. If we're pulling the bottom away from the wall and the top is sliding down, what's happening is the base is changing, dx dt is changing 0.6 feet per second. So that's dx dt because you're pulling the foot of the ladder away from the wall. Now it says how fast is this top of the ladder sliding down? That's dy dt. This is our unknown. When the foot of the ladder is 6 feet from the wall. Okay, so this 6 feet from the wall bit will come into play here as well in a second. So as we get started here, I need an equation. Pythagorean's theorem looks like it'll work perfect. So my equation that I want to start with here is x squared plus y squared equals 10 squared. Or x squared plus y squared equals 100. So I'm using Pythagorean's theorem. Now I'm not asking anything about area, so I'm not interested in the area of this triangle that's formed. I'm interested in this variable x and this variable y. As one changes, the other changes as well. Okay, so let's see what we can come up with when we take our derivatives. So I want the derivative with respect to time of x squared plus the derivative with respect to time of y squared equals the derivative with respect to time of 100. Now really I'm just taking the derivative of both sides, but that derivative would just distribute through to the sum of x squared plus y squared. So the derivative of x squared is 2x, but I just took the derivative with a variable other than t and interest, so I tack on that dx dt. The same for the 2y dy dt. And of course the derivative of 100, the derivative of a constant is 0. So here's my equation. This is my related rates equation. I'll make sure I note it this time. Now what I want to do is I want to figure out what variable I'm solving for. dx dt I have information about, dy dt is what I'm actually trying to solve. So let's go ahead and plug in. We have 2 and then times x. Now the x that I'm looking for here is that 6 feet from the wall. So they're telling me 6 feet is where I'm interested in. So here's that 6 feet from the wall. Now this is plus 2 times y. I don't really know anything about y. I'm going to have to figure that one out here in a second. And then this dy dt is my unknown. And of course this is set equal to 0. Now I do have quite a few questions here. How do I figure out y? Well, y follows from Pythagorean's theorem. 6 squared plus y squared equals 10 squared. Y squared would equal 100 minus 64. Y squared is 36, so y is equal to plus or minus 6, but of course 6 would make sense here because it's a height. It's in the positive direction. So this would be 6 feet right here. Now again, I'm trying to solve for dy dt. So I have 2 times 6 is 12 feet. Plus, oh, wait a minute, that doesn't look right. Let me see. Okay, it's right up here. I think I must have anticipated my answer. 36 is subtracted over here. 100 minus 36 is 64, and the square root of 64 is 8. Okay, so this is going to be 8 feet. Okay, so this would be 8 times 2 is 16 feet dy dx. And this is equal to 0. So to get going, we would go ahead and subtract 12 feet from both sides. So we'd have 16 feet dy dx, and again dy dx is the rate that the ladder is sliding down the wall. I'm sorry, this is dy dt, just copied it down wrong. And this equals negative 12 feet. Now to finish solving for dy dt, I would go ahead and divide through. But there's one thing that we forgot to have in here. Here's my 2 times x, 2 times 6. I forgot to put in that dx dt. And that was information that was given. dx dt is 0.6 feet per second. So I'm going to sneak that in right over here. That's 0.6 feet per second. Okay, so that's going to change this a bit. So 2 times 6 is 12. 12 times 6 is 72. So this would equal 7.2 feet squared per second. So I'd subtract 7.2 feet squared per second. So over on this side, I would also subtract 7.2 feet squared per second. And then to finish this problem off, I divide through by 16 feet. So what's happening on the left, I have that dy dt. That means what is the rate of change, or how fast is it sliding down the wall. And here I have a negative 7.2 divided by 16. And that would leave me with 0.45. Feet squared over feet would be feet per second. Now I think I have something I need to compensate for here. Let's go ahead and look up again. It says that this is sliding down the wall, 0.6 feet per second, so it's sliding down the wall. So I think this should have been a negative. Let's clean this up a bit. And over here, this will be a negative 0.6 feet per second, which would make this a negative, and then I'd end up adding to both sides. And I'd have 7.2 feet squared per second divided by 16 feet per second, and I would end up with that positive 0.45 feet per second. So that's the rate of change that we're looking there. So again, I had to kind of fix things up a little bit. I had to remember that was dropping. So it was moving in the downward direction, so I needed to compensate for that. So there's a lot of little detail things here that you need to make sure that you're keeping an eye on. Another thing that you want to make sure that you keep track of are units. In the next problem we won't have a problem or an issue with units, but we definitely can in some of the problems coming up. Okay, let's go ahead and look at our next one. For our next problem, we're looking at a pile that's being created, and specifically they talk about it's a conical pyramid basically. So let's go ahead and read through it. We'll draw a picture and then we'll try and figure out what's going on. Okay, so it says sand falls from an overhead bin. Okay, so the bin, it doesn't give us a specific shape, so I think we could just draw some sort of an overhead bin like such. So sand is coming from here and it accumulates in a conical pile. So this conical pile basically is a cone, like an inverted cone. And it says the radius of this conical pile is always twice its height. And the height is this vertical distance. If we drop an altitude from the top to the center, that's our height. So we have a couple of pieces of information here. It says suppose the height of the pile increases at a rate, so the change of the height of the pile with respect to time is 1 centimeter per second. So again, suppose the height of the pile increases, so dh dt 1 centimeter per second. It says when the pile is 15 centimeters high, this is what's happening. So when h is 15, this is its rate. It says at what rate is the sand leaving the bin at that instant? Okay, so if we want to try and figure out what that is, we're trying to figure out with this dh dt already given to us, we're looking the volume where this is occurring. So we're looking for the volume, so dv dt. So this is our unknown. So to get started here, we need basically the volume of this conical pile. So when we write the volume of a cone, this would be 4/3 pi h cubed. Okay, so now we want to come up with our related rate equation. So we take the derivative of both sides, so the derivative with respect to time of the volume, the derivative with respect to time of the 4/3 pi h cubed. Now remember, the 4/3 and the pi are constants. So we go ahead and take the derivative of both sides. On the left-hand side, I'd end up with dv dt. On the right-hand side, I have the 4/3. I bring the 3 down, pi I'll drag along, decrease the exponent by 1, and then I need to remember I took the derivative with respect to a variable other than t, so I need to tack on that dh dt and simplify. So the 3's cancel, and I can write my related rate equation now. So dv dt is equal to 4 pi h squared dh dt. Now our unknown is the dv dt, so that works out pretty well. That's already on the left. So I have dv dt equals 4 pi. Now the h, we're trying to be given some information about the h here. So when I'm plugging in values, remember that rate was occurring when h was 15. So this was 15, what do we have here, centimeters squared. Okay, now the dh dt was this change in height with respect to time. This is 1 centimeter per second. So I have everything plugged in here, and let's see if we can simplify. So I have dv dt equals, okay, so 15 squared is 225. 225 times 4 would be 900 pi centimeters cubed per second. So this is the rate at which if you want to think about it, the conical pile is increasing, but it's also the rate at which the bin is being drained, centimeters cubed per second, 900 pi centimeters cubed per second. So again, these are reasonable problems to set up on a test or a handwritten homework. So make sure that you take the time to double check through these pretty carefully. You don't want to always rely on the help me solve this all the time. You want to be able to come up with your own method after looking at several examples. For our next one, we're going to be looking at another triangle shaped problem, but there's quite a bit more to this one. Okay, so there's quite a bit going on with this one. It says a hot air balloon is 140 feet above the ground. So let's go ahead and start with that. Now, I'm not a great artist here, so here's my hot air balloon. It doesn't even look like one. But the hot air balloon is 140 feet above the ground. And then we have this motorcycle that's coming along in this direction. And this motorcycle is traveling in a straight line on a horizontal road, so it's following this line right here. It passes directly underneath the balloon, and it's going 30 miles per hour, which is 44 feet per second. Now if we read for this, feet, everything is in terms of feet, so I'm going to ignore this miles per hour and I'm going to stick with the 44 feet per second. So what this is, if we want to think about this direction, this would be in the x direction. So the direction dx dt, they're telling us, is 44 feet per second. That's how fast that motorcycle is going when it hits right directly underneath the balloon. Now, what happens is the motorcycle keeps going and the balloon keeps rising, and they want to know what is the rate of change of the distance between the motorcycle and the balloon 6 seconds after this. Okay, so let's draw another picture 6 seconds later. So 6 seconds later. Well, the balloon is going to keep going higher, and I'm going to kind of run out of space here. We'll say this is my balloon up here. And what is this new height? Well, it was 140, but then it kept rising, and it's rising at a rate of 14 feet per second, and it traveled for 6 more seconds. So 140 plus 14 times 6 is going to give us that new height of 224 feet. Now the motorcycle keeps going as well for 6 seconds. And so for 6 seconds, this distance x is 44 feet per second. So that's 6 times 40 is 240 plus 24 is 264 feet in 6 seconds. So the motorcycle is now here. And the question is, what is this distance doing? How is that changing as the balloon rises and the motorcycle keeps traveling? So we have this height. This height is y. This height, or this length, is x, and then we'll call this third side z. And we can see clearly that we have Pythagorean's theorem here. So let's go ahead and write out Pythagorean's theorem. X squared plus y squared equals z squared in this particular case. Now what I want to do is take the derivative with respect to time. So I have 2x, and again this is d dt, I'll write that on the next line, d dt of x squared plus d dt of y squared equals d dt of z squared. Now for each one of these I'm taking the derivative of a variable other than time, so I'll have to remember that implicit part. So this equals 2x dx dt plus 2y dy dt equals 2z dz dt. So we have a lot going on here. Now I can start kind of filling in the blanks here. So I have 2 times x is 264, and then dx dt is the speed of the motorcycle, so that was 44 feet per second. I need to put in my units here, so make sure I have my proper units. So this would be 44 feet per second plus 2y, y was 224 feet, and it's rising at a rate of 14 feet per second, I believe. Yep, 14 feet per second. So this is going to be dy dt, is that 14 feet per second. equals 2 times z, and then this dz dt is what I'm actually trying to find, but I don't know what z is. Well, let's look at our picture here. If I know two legs of a triangle, I can find the third triangle, and it's especially easy if it's a right triangle. So this would be leg squared plus leg squared equals hypotenuse squared, or I could use this x squared plus y squared equals z squared. So this is 224 squared plus 264 squared equals z squared. So as I'm simplifying this, I get z squared equals 119,872. Now this is the kind of problem I wouldn't expect you to do on exams because our numbers are getting so huge, and we also need an approximation for the square root of that, and the square root of that would be about 346.23. Now the more you round at this step, the more error you'll have in your final answer, so don't over round here. And of course this is feet. And so that number is going to go in right down here, 346.23 feet. Okay, so let's keep simplifying. This one's a long one. I think we're going to use up more space than we might expect. So over here on the left, I'll have my 2 times 264. Plug it into my calculator here, times 44. And I'd have 23,232 feet squared per second. Plus 2 times 224 times our dy dt. Now our dy dt was the 14 feet per second, and I think I said it but I didn't write it down. So as we plug that in, that would be our 14 feet per second. So I'm going to take it times 14, and I'll have 6,272 feet squared per second equals, and then on the right hand side I end up with 600, almost 700, but 692.46, and this is just feet. And of course I have my variable that I'm trying to find here is dz dt, that distance. So we have some simplification that we need to do here, so once again algebra comes in handy. On the left hand side of the equation I would add the 23,232 plus 6,272, and I'd end up with 29,504 feet squared per second equals the right hand side, 692.46 feet, and this is dz dt that I'm trying to solve for. Now I want the dz dt to stay, and I want this to go, so I'm going to divide both sides through by 692.46 feet. 692.46 feet. And I end up with feet canceling, so I'm left with feet per second. So dz dt, that change in distance between the hot air balloon and the motorbike, would equal 29,504 divided by the 692.46, and I end up with dz dt equals 42.61 feet per second. Now this is not how far apart they are, this is the change in their distance apart at 6 seconds. So this one we had to do a couple things. We needed to remember that everything needed to be in terms of feet, and then we also needed to see the change in that triangle shape from the original position of the motorcycle right underneath the hot air balloon, and then what happens 6 seconds later. So drawing a picture is always very helpful. So this next one also involves a triangle, but we do have a fixed height on this one. So we don't have the same variables that we did on our last example. So you have to be careful how you read these. So we have an angler hooks a trout. None of this sounds like a triangle right now, but after we read through it, hopefully it will. An angler hooks a trout and reels his line in at 5 inches per second. Okay, so this is some sort of a rate. This is d something to time is 5 inches per second. Now I'm not sure what that rate is yet. We'll have to see what the rest of the picture looks like. Assume the tip of the fishing rod is 11 feet above the water and directly above the angler. So we have this person fishing. And again, I'm not a great drawer or great artist here. And the fishing pole is straight above their head. And the total height from here to the water to above his head is 11 feet. So this isn't changing. When he's reeling in, and of course the fishing pole is not on his head, but when he's reeling this in, he's not moving the pole up and down or back and forth. It's just straight above his head. So this is some information that we have. And it's again directly above the fisherman. The fish is pulled horizontally, so the fish is it's underwater and it's being pulled toward the fisherman. It says find the horizontal speed of the fish when it is 16 feet from the angler. Okay, so let's draw out some couple things that we have here. We have this distance x is 16 feet. I see kind of a problem here. This is inches per second. So we're in terms of inches. And then all of a sudden, I start talking about 11 feet above the water and 16 feet from the angler. So I think what we probably better do here is convert everything to the same unit. So this is 5 inches per second. Let's go ahead and convert everything. So 11 feet would be 11 times 12 would be 132 feet. So we could think about that as 132, I'm sorry, not inches, or feet, not feet, inches. That's why we just converted it. So instead of 11 feet, we'd have 132 inches. Now down here I have 16 feet, and 16 times 12 would be 16 times 10, 160 plus 192 inches. So this would be 192 inches. So this little fish is coming in, has a hold of the line, of course, and is coming in this direction. So let's see if we have everything here. So we're going to call this x because it's horizontal. We'll call this y because it's vertical, and let's call z, and this is the distance from the fish to the tip of the pole. That's going to give us that information here about the line coming in. His line is reeling in at 5 inches per second. Okay, so that's dz dt is 5 inches per second. So as we're setting this up, it looks like to me our equation, this is our right angle here, would be x squared plus y squared equals z squared. Now on this one it's a little bit different though, because we know the height of the fisherman. So the height of the fisherman and the pole is 132 inches. So this would be x squared plus 132 squared equals z squared. Now the fish is moving, so I can't say that that's fixed. This is a fixed height of 132 inches. So this would be my initial equation. Now I'm getting nervous, I forgot to write related rate up here again. Yep, so this one here would be my related rates equation. And again, I keep going back to make sure I specifically name that, because a lot of times in your homework it specifically asks for it. Well, we need to come up with a related rates equation here, so I'm going to take the derivative of these with respect to time. So the derivative with respect to time of x squared plus the derivative with respect to time of 132 squared equals the derivative with respect to time of z squared. Okay, so as we take that derivative then, I end up with 2x dx dt, because I take the derivative of x squared to get 2x. This is my implicit part. I took the derivative with respect to a variable other than t, so I need to tack on that dx dt. Now this one is just a derivative of a constant. So 132 squared is just a constant, and the derivative of a constant is 0. I'll hold that in here. And then on the right hand side, the derivative of z squared is 2z, and I took the derivative with respect to a variable other than t, so I'll tack on that dz dt. Okay, so let's write out what we have here. We have 2x dx dt equals 2z dz dt. Okay, so x was that horizontal distance, and from our picture that x was 192 inches. So 192 inches. Now dx dt was the speed that we're looking for. It says find the horizontal speed of the fish. That was dx dt. So this is our unknown. So I'm going to put that in a different color so we don't forget that that's what we're trying to solve for. Now as we're looking here at the rest of this, I should be able to figure out what z is. And then that dz dt is how fast the fish is being reeled in, and that was the 5 inches per second. Now how do I figure out that z? Okay. Well, it looks like to me I have a nice little Pythagorean theorem set up here. So I have 132 squared plus 192 squared equals z squared. So if I'm trying to figure out what z is, I'd end up with z squared equal 54,288. And of course, taking the square root of both sides, I get z is approximately equal to 233.04 inches. So that's the number that goes down here for z, 233.04 inches. So let's go ahead and multiply these out. Now, if you wanted to catch this real quick, you could see that I have a 2 on both sides, so I could divide that out. So you know, I'm not even going to multiply these. I'm just going to divide through. So what ends up happening here, I have canceling occurring, then I end up with dx dt is equal to, on this side, the 2's canceled, and not that it matters if you have a calculator, you just crunch this through anyway. We'd end up with 233.04 divided by 192, and I end up with, let me double check this on my calculator, 6.07. And then my inches cancel, so I'm left with the inches per second. So that's how fast, that's that horizontal distance or that horizontal speed or rate at which the fish is being reeled in. So that's the horizontal speed of the fish when it's 16 feet from the angler. So again, a good picture helps here, and it also helps to figure out what's constant and what's variable. So this section is pretty interesting. I like it because there's so much going on in terms of derivatives and plugging in values. Some of the most important things you can do is not skip steps. Make sure you put in all of your units. They're important, and they also help you make sense of what your solution is and if your solution seems correct. As usual, if you have questions, please let me know. You're welcome to take a screenshot of the problem and text it to me, or you can also use your Pearson Connect option. Good luck!